Yeah, it's working. So next speaker is Marco Gorghetto, and he's going to talk about the cosmic string distribution to the axion relic density. Say yours.
Okay, thank you. Can you hear me?
Yep. Yeah. Okay.
Because I had some connection problems before. Hopefully it won't happen again. Anyway, okay. So thank you very much, especially for the invitation. So today I'll be talking about some work in collaboration with Ed Hardy and Giovanni Vildodo on axions from strings, and the talk is based on these two papers, the second of which came out just a few weeks ago. So our goal is to calculate the QCD axion relic density in the so-called post-inflationary scenario, where it's determined by decay of topological defects, which are cosmic strings and domain walls. So the problem we are addressing in these papers is actually very important theoretically, because besides giving us an understanding of the physics of the axion field in the scenario, which is actually yet far from being completely understood, so this scenario actually predicts a unique value for the QCD axion mass. And this value is probably one of the most important information that theories can provide in the experimental search for this particle, and also will be crucial in order to interpret the results from experiments. So as I will see, we give for the first time a convincing proof based from first principles, so based from numerical simulations, that strings emit a large amount of axions, and this will pin down the axion mass to values of the order of the milli-electron volts, so 10 to the minus 3 electron volts, and therefore restricting a lot the allowed parameter range for this particle in this scenario. Okay, this was the introduction. So let's start. So as you know, the QCD axion is the most robust solution to the standard model solution problem, and also provides a natural dark matter candidate, and is also naturally and automatically produced in the early universe. However, the actual dark matter abundance depends on the cosmological scenario. In particular, depends on the hierarchy between the inflation scale and the axion decay constant, Fa. In any case, if Fa is larger than the maximum between the Hubble during inflation and temperature rating, whatever are the initial conditions of the axion field in the early universe, due to the exponential expansion of the universe during inflation, the axion field will get smoothed out over distances which are much larger than the Hubble horizon during inflation. And therefore, the field will be practically constant every each Hubble patch, acquiring an initial value, A over Fa, theta 0, between 0 and pi. And the relic density can be calculated in terms of the so-called misalignment mechanism. However, depends on this initial misalignment angle theta 0, and not only on Fa. And therefore, the scenario is not really predictive in terms only on the Lagrange parameters. On the other hand, if Fa is smaller than the maximum between the Hubble during inflation and temperature rating, also known as a post-inflationary scenario, the axion field has random fluctuations over what would be today's observer horizon, and there are actually no free parameters in the initial conditions, and therefore the axion relic density should be only a function of the only free Lagrangian parameter, which is Fa, and therefore requiring that this relic density also equals the observed dark matter relic density. This corresponds to a prediction for Fa, or equivalently a prediction for the QCD axion mass. And as I said at the beginning, this number of Fa or the axion mass is very important for experiments if the scenario actually took place. And actually, if an axion with this mass is discovered, besides having an explanation for the dark matter and the strong state problem, we will also have a handle on early universe cosmology, because we will know that Fa should be smaller than the maximum between Hi and Tr. If instead the axion is discovered but at another value of the mass, the scenario will be ruled out. But still, we will get some information about early universe cosmology. In particular, we will know that the pre-inflationary scenario would have happened, in particular that the axion was homogeneous in the early universe. So, in any case, there is a strong motivation to understand better the physics of the scenario and the value of the axion mass. So as I said, in this scenario, the axion has random fluctuations over the observer horizon, and is periodic. Therefore, there will be in general field configurations where the axiom wrap non-trivially the fundamental domain minus pi and pi, like in this blue circle. And if you sync the circle to a point, by continuity, there should be at least one point inside the circle where the axiom field is not defined, or if you want, where you guess all the values between minus pi and pi. And if you do the same reason in the whole space, there will be a line of points where this happens, and this configuration is called Axion string, and will be generally present in the universe in this scenario. So strings have a core string called string core size, which is of the order of the inverse of MR, where MR is the mass of the heavy radial mode, of the heavy modes that UV complete the axiom theory. And in the case in which the axiom theory is just UV completed by a single Pechenqui field with a maximum potential, this MR is also the mass of the heavy radial mode of this Pechenqui field. And if the maximum potential has order 1 parameters, this MR is also of the order of the axiom theory constant, Fa. So strings actually store quite some energy in them, and this energy is usually expressed in terms of the so-called string tension mu, which is defined to be the energy of a string per unit length. This tension is given by two contributions: one pi Fa squared coming from the core, coming from the fact that there are points in space where the radial mode is on top of the maximum potential, and therefore contributes non-trivial to the Hamiltonian. And then there is another contribution coming from the axiom gradient, by the fact that the gradient of the axiom field is not vanishing at arbitrary large distance from the center of the string. This the contribution is actually logarithmically divergent for a single string, and for a configuration of strings, this contribution is cut off at the distance between two strings with opposite orientation, which in the universe is over the Hubble, inverse Hubble. And so the string tension in the universe is over the pi K squared times log over MR over H. So after they are formed, the strings after they're formed, although the strings are stable by themselves, when attacked together, they can interact between each other. They can form loops that can shrink, or bands that can shrink. And the result of this process is called string recombination. And so this process is called string recombination. And the result is that the energy that is stored in the strings is emitted and is converted from strings into axion radiation, or just axion waves, which then make up a part of the axions we observe nowadays. So I would just call axions just axion waves. So once formed, these strings enter a so-called scaling regime, which is defined to be a regime where there is an approximately constant number of strings per double volume. And the reason is the following. So as the Hubble parameter diminishes, the Hubble horizon grows, and the strings that were previously disconnected between each other enter into each other's horizon. And as a result, they will have some dynamics, and they will start annihilating. And you expect them to enter a sort of equilibrium, such that the rate at which strings enter into each other's horizon is balanced by the rate at which strings disappear. In such a way, the number of strings per double volume is approximately conserved. As we'll see, the scaling regime, which plays an important role in our discussion, is also an attractor solution in the sense that it's reached independently of the string density in the initial conditions. So it will be asymptotically reached in the universe. So the situation is the following. When the temperature of Hubble over the Fa, at which the log over mile of H, which you can think of log over Fa of H is between 1 and 15, a configuration of axion strings would form as a result of Pechenqui symmetry breaking, or a quantum configuration during inflation. And these strings then enter the previously mentioned scaling regime, in which there is an approximate constant number of strings per volume. And this scaling regime lasts for a long time in log units until the log over H is 70, at which time the Hubble is awarded of the axion mass, and the temperature of the universe is awarded lambda QCD. At this time, the axion potential becomes cosmologically relevant, and a network of domain walls forms attached to strings, And for the system of strings and domain wall, it is more convenient and energetic to just decay into axions. So during this whole process, in particular during the scaling regime, and during the time of the domain wall formation and annihilation, axions are emitted from strings and domain walls, and they will contribute to the relic axions we observe nowadays. So this video shows the evolution of a system of axion strings, and the cube here represents the Hubble horizon that increases in time. So although the total number of strings diminishes, the length of strings inside the Hubble volume is actually almost constant in time, and this is the result of the fact that strings collapse as soon as they enter the cosmic horizon. And as you can see, the dynamics of the system is quite hard to capture analytically, and most likely this kind of numerical simulations are needed to fully understand the evolution. So unfortunately, numerical simulations can't scan the whole evolution until the log over of h is equal to 70, at which time domain walls would form. And the reason is the following. So in order not to incur numerical effects, there should be a few lattice points inside the string core, which is represented in red, and there should be a few Hubble patches represented in blue in the box. And this means that log over of h, which should be 70 at the Euclidean transition, is only bound to be at most the log of the ratio between the cube and the circle, which is 7 or 8, since in the lattice they can be at most 5,000 points with nowadays numerical capabilities. And as a result, of course, with numerical simulation cannot study directly the whole evolution. So this means that actually we have no hope of analyzing the dynamics of the destruction of the network at the QCD scale. And therefore, we need to content ourselves with a less ambitious goal, which is to calculate only the axions produced during the scaling regime. So, and even in this case, we still can't directly reach large logs, but at least we have an advantage that the scaling solution, where the properties have precise scaling laws. So the idea is the following. The simulation can run between log over of h between 1 and 7, and there should be enough time in the simulation to understand and extract the properties on the attractor solution, in particular the number of strings per volume and the rate of emission to axions. And then, since this attractor solution has a precise scaling law, we are able to reconstruct this attractor until the physical point, which is log over of h until 7. And this would give a lower bound on axions from the scaling regime. Of course, this will give a lower bound on the abundance. In particular, we'll neglect the axions that are emitted from at the time log over equal to 70 over h equal to 70, which are emitted by string domain wall collapse. These axions, which should contribute positively to the number density of the final axions, will be neglected. However, they may or may not dominate the final abundance. So in order to complete this program, calculate the number density from the scaling regime, we need essentially 3 ingredients. First of all, we need to know the energy of axions, which is emitted per unit time from the network. And this, by the fact that there is a scaling law, and by the fact that by just energy conservation is determined more or less only by one parameter, which is the number of strings per volume psi. On top of this, we need to know what is the axion number density, the least in the process, and this is determined by the axion energy density spectrum, which just tells us how the energy density in point 1 is distributed in different wavelengths. And at the end, we need to understand how the number density, which is produced between log 1 and 70, is transmitted during the nonlinear evolution that happens at the QCD transition. Indeed, the number density produced before log equals 70 will be a relativistic number density because the axions have no mass at the point. At this point, the axion potential will turn on, but since it's not linear, it could have an non-trivial effect in the evolution of the number density before the number density becomes non-relativistic and conserved per moving volume. So I will now describe these string gradients in detail. So first of all, let's start with the number of strings double volume, psi. This determines the energy that is emitted from strings into axions. And this is defined to be the string length in one Hubble volume, units of a Hubble radius, average over all the Hubble volumes in the universe. So for example, this configuration of psi equal to 1, this 2, and so on. Actually, psi is probably the most clear observable that shows this attractive behavior. And indeed, I show here the evolution in time of psi as a function of time, which is represented by the log of MR of H. For two systems, the physical system, which is the important one, and the fast string system. This fast string system is just the physical system with the mass MR changed in time, like 1 over the scale factor. And this system turns out to have better numerical properties, but of course is unphysical. Therefore, to get numerical predictions, we study the physical one. And as you see, despite there is a huge range, so the initial conditions have a number of string double volume that ranges of many orders of magnitude. In both cases, and most clearly in the fast string case, the number of strings tends asymptotically to a common value, and this is the first manifest proof. Of course, it's only numerical. That of the existence of an attractor solution, which is independent of the density of strings in the initial conditions. So, although different conditions tend to a common value, this common value does not seem to be constant in time. And indeed, here I show the same plot, but on linear scale for the physical system, where it is manifest that psi grows logarithmically in time on the attractor, which is shown in black. And this linear growth actually corresponds to a scaling violation, which means that the scaling parameter depend on time, in particular logarithmically on time, which is expected since many properties of a network, including the tension of the string, depend on time. And this linear increase, linear log increase in time, is even more evident in the fast string system, which is shown here, where any reasonable nonlinear function of log is a bad fit to the black points. So this gives a numerical proof that there is a logarithmic running of a number of strings double volume, which is actually which is a non-trivial statement. So the scaling violations can be very well fitted and parameterized by this formula, which is a linear log growth plus 1 over log corrections, and of course at large log, which is the physical point, only the linear growth would be important. And this would imply at log equals 70, a number of strings double volume, which is about 15, and is quite larger than what can be achieved in simulations. So on top of the fact that there are logarithmic violations in the tension of the strings, there are actually some other hints that show that this logarithmic growth is not going to stop. First, there is no additional scale in the problem. Therefore, it's expected that this growth is not stopping anytime soon. And then, actually, the system of global strings, which is Axion strings, is expected to tend asymptotically at large log to a system of Number-Goto strings. And the simulations on Number-Goto strings actually show a much larger value of psi. And this shows actually that this growth will be compatible with the fact that the system of global strings tends to Number-Goto strings. So as a second ingredient, we need the Axion energy density spectrum, DRA indicated T. And even before looking at the results from the simulations, we can guess of the general form of the spectrum. So here I show the spectrum as a function of the momentum. The spectrum should have a cutoff at momenta which are smaller than Hubble because of causality, and at momenta which are larger than the inverse of than MR, because the inverse of MR is the small scale in the problem. And the spectrum should have a peak at momenta over the Hubble, because the strings have average curvature over the Hubble, and that you expect them to emit wavelengths over the Hubble to the -1. And in between, since there is no scale between h of MR, the spectrum should be approximated by a single power law, which we call 1 over k to the q. And q is also called spectral index. And this q determines the hardness of the spectrum, which means that whether the spectrum is UV dominated or IR dominated. So if q is larger than 1, the spectrum is IR dominated, and it has a broad peak at the moment over the Hubble, and most of the energy is emitted at the moment over the Hubble. On the other hand, if q is smaller than 1, the spectrum is IR dominated, and most of the energy is emitted at momenta over the MR over phi, which are UV momenta. And in the first case, most of the energy is stored in axions with small momentum, and there is a large number of them. In the second case, instead, most of the energy is stored in few axions, which are UV with momentum over the phi. And for obvious reasons, in the second case, the number density of axions, which is defined this way, is exponentially suppressed compared to the previous case, is e to the minus 70 suppressed. So is it therefore very important to understand whether the spectrum of axion symmetry is UV or IR dominated. And finally, since there are many properties of a network that depend on log, in general, we could expect a dependence on this Q, this power law Q, which is also spectral index. We could expect this to depend on log. So this is the result from the simulation of the spectrum, and all the general features are met. In particular, there's a cutoff at momenta smaller than Hubble, smaller than 510 Hubble, and then there's a cutoff at momenta which are larger than MR, in particular MR over 2, and in between, you can find that the spectrum is actually a power law, which, however, does not seem to be constant in time as expected. And if you actually measure this power law, you find the following plot. So this is the spectral index as a function of time represented by log. And although the spectral index is less than 1 during the whole range, a non-trivial landing is evident as expected. And this corresponds to a spectrum that is becoming IR dominated at log equals 17. So although the spectrum is UV dominated at small log, in particular during the simulation, it will become IR dominated at log 17. Actually, it will become IR dominated much before 70, maybe at a log around 9, which is just after the reaching of the current simulations, but maybe can be reached in the near future. So this running on Q implies that so the most conservative extrapolation of this running of Q implies that Q is larger than 1 at log equals 17. And actually, these lines can be fitted very well with just a linear function. So finally, we want to notice that even if Q is, so as long as Q is definitely larger than 1, the number of axions is not very dependent on the shape of the spectrum and on the numerical value of Q. So we don't actually need to know what is the precise value of Q at log equals 17. And so we don't actually need to understand what is the exact extrapolation of this line. And the fact that Q is larger than 1, which is not which in the simulation, but is expected to happen at large log, also meets a theoretical expectation based again on Numerical strings. These Numerical strings, when coupled to an external axion field radiation, would oscillate many times and emitting only wavelengths which are of the order of the initial loop size, which is over the Hubble, and therefore having a spectrum which is a UV limit. So the simulations are the first nice proof from first principles that this limit is actually reached, and they tell us how this limit is actually achieved. So last, we need to understand what is the number density after the linear regime that happens at the exclusive transition. So we understood that at log equals 70, when the system of axion string is destroyed, the number of strips above volume is about 15, and the spectrum is IR dominated. And the spectrum of axions would have would be so these axions would form some waves that have oops, sorry, thank you, that have n. Oops, I'm not gonna go and hide anymore. Oops. So at h equals ma, which is h star, which we define as h star, the waves produced up to h star, during the scaling regime produce a contribution to the energy density in terms of waves, which is of the kind of psi mu over t squared, which if you just write t in terms of Hubble and mu in terms of log, this is of the kind 10 to the 3 for xi log of 10 to the 3 times h squared of fa. And these waves actually store an energy density which is stored in the gradient, which is much larger at h star than ma squared fa squared, which is the usual energy density that is stored in the pre-inflationary misalignment, except for the theta zeta squared, and is also of the same order as the potential energy density, since the exponential potential is a cosine and therefore is bounded. As a result, since the gradient energy is much larger at h star than the potential energy, this means that the Hamiltonian density of the system is only dominated by the gradient terms, and the potential is negligible, and the field evolves like if no potential was present. So after h star, the field continues to redshift relativistically, and therefore its amplitude will just go down like 1 over the scale factor. So the energy density will just go down with the scale factor to the 4th. In the meantime, the mass grows, and the potential will grow. And this period of relativistic redshift will end at the time when the two are comparable. So this dynamics is in contrast to the usual misalignment mechanism, which instead has an axion field which is in the non-relativistic regime soon after h star. So this field of redshift lasts until HL, which is the time at which these two are comparable. At which time we need to actually solve the equation of motion numerically, because the potential is not linear. But however, after an nonlinear transient, we expect that the field settles down around the minimum, and the number density of non-relativistic axions is conserved. So, despite this nonlinear transient, we can give an analytical prediction for the number density that turns out to be actually remarkably accurate. So the number density of non-relativistic axions at this time, HL, is given by rho A over MA, where MA is the axion mass at HL, which has in the meantime grown. And this axion mass is determined by equating these two quantities. It's given by square root of log xi log msh. And this therefore gives the plugin rho A, this expression, an enhancement of the number density of the kind square root of xi log h fa squared, which is about square root of xi log larger than the misalignment, which is h fa squared. So the final number density is larger than the misalignment of this factor, but however is a bit smaller than the energy density at h star, which is enhanced by a square root of by xi log, and this is because this period of relativistic redshift diminishes the number density because the field redshifts more, and because the axion mass has grown in the meantime, and therefore more energy is required to produce each axion. So just to say, I wouldn't have time to spend on this, but at h star, the dynamics of the axion waves is quite richer than what I just described, since at h star the A over Fa is larger than 1, is actually much larger than 1, is over 10, and therefore the amplitude of the field is much larger than Fa. And this means that since the axion is periodic, the axion consists of a superposition of waves that wind and unwind many times the fundamental domain, like this. And therefore from domain walls, but these domain walls are actually topologically trivial because they connect the same vacuum, which is at equal to 0, but anyway present. So actually at H star, the field looks like this. The waves. So here the field is represented in the domain minus pi and pi. 0 is green, which is the minimum. Pi is yellow, minus pi is blue. In between, the field overtakes one domain, and in between there is a domain wall. However, these domain walls at this time are not relevant because the exponential is negligible, as I said. So during the subsequent evolution, the field and domain wall evolve freely during the relativistic regime because the potential is negligible, while the average energy density, the average axion amplitude will drop. So at the time of when the potential is equal to the kinetic energy, these domain walls will collide and will form what are called oscillons, which, however, are small objects that don't affect much the number density of axions, and everywhere else the axion is in the linear regime, and we can calculate the non-relativistic number density, which is conserved. So in this plot, I show the number density calculated in the previous nonlinear simulation, normalized to the Museline number density at theta 0 equal to 1 as a function of psi log, which is for the axion 15 times 70. And these points are the result of the simulation of the nonlinear transient. And these lines represent the analytic estimate we made before, by just which was about the square root of psi log larger than Museline. And these different lines correspond to different higher cutoffs of the spectrum, which are about 5 and 10, which is about 5 and 10 for the axion. And as you see, first of all, the analytic estimate is very in agreement with the numerical result. And second, for the QC axion, the number density from strings is announced over a factor of 10 to the 2, 2 times 10 to the 2, compared to the Museline at theta 0 equal to 1. So this agrees both with simulations and with the analytic prediction we said before. And actually, the prediction can be just made not without looking at simulation, but just using our analytic formula. Also, just to say, this nonlinear transient and the relativistic regime have the result of changing the shape of the axion spectrum, making it more UV dominated, and therefore probably changing the subsequent evolution of mini clusters. So finally, in conclusion, I want to discuss the lower bound on the axion mass from this result. So the fact that there is about 10 to the 2 more number density compared to the Museline at theta 0 but 1 means that the axion constant should be smaller, of a factor about 10 to the 2, and therefore goes from 10 to the 12 to 10 to the 10 GV. Actually, there is not really proportional, but it's like a rough order of magnitude. And this means that the QC axion should have a mass larger than about 0.5 milliatom volt for the KSVZ model. The DFSZ model has a stronger bound because of the fact that actually what enters in the number density of axions from strings is not FA, but is the value of the pitching field, which is announced by the anomaly coefficient. And this corresponds to about 3.5 milliatom volt. And as you see, in the scenario, there's still a small window between this point and the supernova bound. And therefore, this mostly motivates to look at this window a bit more in details, and therefore motivates to think about experiment in this range. Finally, I want to say that we are neglecting the number density from domain walls, which is expected to enhance those from strings. And if it is enhancing it, it will make the bound even stronger, and maybe this green band. Oops. On the other hand, if the number density from the walls is negligible, then these are actually predictions for this scenario. So, concluding, we've shown several things. So the system of axion strings is zeroing towards an attractive solution, which there are evidence for logarithmic violations on the number density of strings and the spectral index of the axions emitted. And the most conservative extrapolation implies more axions from strings, and this extrapolation is in accordance with the expectations from the number of strings coupled to the external axion field. Then, due to this nonlinear, the fact that there are so many axions produced, the potential is negligible at exogenous transition as opposed to the pre-inflationary misalignment, and this implies a period of relativity class shift and a nonlinear transient, and this has the result of partially reducing the number density, which, however, still dominates over the misalignment over a factor of about square root of psi log, and making the spectrum more UV. And in this scenario, this implies that the axion mass, in order not to overclose, so not to overproduce such matter, is between 0.5 and 20 millielectron volt. 0.5 comes from dark matter reproduction. This 20 is from astrophysics, particular supernova. Okay, thank you.
Thank you, Marco. So we have time for a couple of questions. Any question? I can start with one. I wonder how much, I'm talking about the scaling regime, depends on the assumption of radiation domination, and how does it change if, for instance, you have a period of matter domination or vacuum domination?
So what actually is important for the number density is that the scaling regime is there just a few Hubble patches before the diffuse transition. So if the scaling regime if the universe is in radiation domination just before the diffuse transition, let's say have a few Hubble patches before, then the results will not change. If instead the diffuse transition didn't happen, or with different cosmology, yeah, the result will change over the one. Okay, so essentially to the last part of the evolution, basically. Yes, because most of the axions are emitted just before the diffuse transitions, and you can see very easily from the scaling of the emission of axions. Okay, Enrico raised the hand, so please go.
Yes, Marco. So clearly, as you clarified, all this applies in post-inflationary scenarios. But I would say, and this is more maybe half a comment, half a question. So this applies to the quantum field theory axiom, because in quantum field theory, the only way we know to make a suitable particle that has no potential is the Boston boson of the U1 symmetry. So then you get strings. But axions can come also from strings, not your strings, but the superstring. And in that case, they come as gauge fields. And they are not related to a breaking of a U1 continuous symmetry. So I would expect that in that case, there are no topological defects associated with strings. Just to open a bit the axion scenario, I expect that besides not applying to pre-inflationary scenarios, this does not apply to axions that come from superstrings, because also in the low energy theory, there is a duality transformation between those antisymmetric two forms and the pseudoscalar axion, so they are undistinguishable. The origin is really different, and it's an origin which is not associated with symmetry breaking. So, yes, a comment and a question.
Is a comment or a question?
Well, do you know anything about this? That's the question.
No, I'm not an expert. So the prediction we make is for for Axions coming from quantum field theory.
In post-inflationary scenario.
Yes.
Okay, thanks.
More questions? Andrew, so please go.
Hi. I mean, I think I had a question that's in similar spirit to the previous two. I'm trying to understand under what conditions do I expect the logarithmic deviation from scaling to arise? Is it unique to global strings, or does it carry over to gauge strings? And if it's unique to global strings, do we understand why it rises here?
This is a question which is open research field. So what happens is that the logarithmic running appears in global strings like this, where the axion where the U1 is not caged, and apparently this similar logarithmic running might happen also in gauge strings, although it's not clear from literature. And at that point, it's a bit hard to explain why this logarithmic running is there, because the tension of local strings or strings is not dependent on this log, because the tension is just localized in the core. So this actually open research. And the naive question is that from what I think, the question is that the answer is that both of them probably grow logarithmically, and most likely this growth is not related to the strictly speaking to the tension, because it seems to be present also in gauge strings. So that's the most. I don't know if I answered.
Thanks. Yeah, it's interesting.
More questions?
Can I ask a question, Marco?
Yeah.
Yes.
Sure.
So, I mean, I want to understand actually how accurate you're doing numerical simulations in that transition region, correct?
Which one region?
Well, right when the mass is increasing, you're ending the you're going over between the relativistic and non-relativistic regimes. Yeah.
So there is an anomalous resistive regime here, which we study, and you can argue that it's not accurate, but we think that it's accurate. So at this time, the field is composed. At this time, log numeric over each equals 70, the field is composed by strings, domain walls, and the axion radiation that is produced up to this point.
So what I'd like to know, Marco, is how well you think you understand that region. That how well under control is that? Because I understand you have this issue of you haven't got the log, to the really in the scaling regime yet. But let me just ask a separate question: is once you're in that transition regime, you can then do a specialized simulation.
Well, we think we understand that well, because essentially the evolution is essentially linear until this point.
Yes.
At this point, there is a very small, a very rapid non-relativistic transient, which we simulated, and after that, very very fast, the field goes again linear, non-relativistic. So actually, this transition is actually very fast, and it probably takes much less time to be studied than the whole evolution, the whole previous evolution. But so again, all this part of the relativistic redshift can be even studied analytically, because there's no potential.
Mm-hmm.
At this point, again, you have to do some simple or not simple numerical simulation. Or of course, in this numerical simulation, you have to neglect strings, because the strings cannot be simulated with the correct values of the parameters.
So that's my question. So Marco, can you tell me a little bit more, when you're doing that regime, that nonlinear transient regime, what you actually put on? You do a numerical simulation that involves just
we do a numerical simulation of only the axion field. It's only the axion field, and we use as initial conditions the waves that have the spectrum that is emitted at the scaling regime up to log equals 70. So it's like would be the reconstructed spectrum that we think the strings the field would have at that time, and this spectrum is reconstructed essentially by assuming the psi grows logarithmically until log equals 70, and the spectrum is IR dominated. And both of which assumptions seem to be very reasonable. In particular, the fact that is IR dominated is probably very reasonable, and the fact that psi is logarithmic is also reasonable. But even if it's off of a factor of 2, say, the result will not change. So there, it's pretty solid. The result is pretty solid, at least in this part. Also in the other parts, but at least in this.
Okay. All right. Thank you.
There's a question in the chat from Keisuke Rigaya. I will read it for you. So Keisuke asks, would you mind explaining the origin of psi much larger than 1, which is larger than the expectation from causality and the official string reconnection? Do the reconnection probability become small, so large log?
Sorry, I don't see the chat. Can you say that again?
Yeah, so would you mind explaining the origin of psi much larger than 1, which is larger than the expectation from causality and efficient string reconnection?
There is no expectation from causality that tells you that psi is not much larger than 1. Why is that?
I assume because you would expect one string parabol patch.
Well, if strings don't interact efficiently, you expect them to grow more. So it may be, and probably is the case, that as time goes on, this log increases, and the inertia of the strings increases logarithmically. So as time goes on, the strings are a bit more heavy to transport or to move, but this is only logarithmically. So you expect that they group a bit more in one number patch. And in the limit of infinite log, actually, these strings are infinitely heavy, so they cannot move, and therefore they will. Actually, this is a nice connection with the Number-Goto strings. Number-Goto strings don't cut, so are just free strings, and these free strings cannot annihilate, so they will just stay free. And if they stay free, means that they just remain fixed in moving coordinates. And while the abel horizon grows, their number would increase in the horizon like indefinitely. So if you want, it's like the strings would decouple from the axion at large value of log, and this means that they would gather more and more inside the abel patch until at infinite log, they would be essentially infinite. The Clyde would be infinite. I don't know if I explained well.
Okay, I think it's clear. Okay, I would like to close the session and thanks all the speakers and all the participants for the nice discussions. And well, see you next time. Bye.
Bye.
Bye. Thank you.
Bye.
Goodbye.